Of course, the cornering behavior or the turning behavior will be mostly about the forces in the y direction, which will cause a rotation around the center of the vehicle. And these are the lateral forces. So these lateral forces are, of course, described earlier also in the tire behavior model. To track this behavior, we will also save the y forces. So we also add here the block to save the y forces, Fy forces saved to the workspace with the structure with time format. On the other hand, it is especially interesting to track the turning behavior as the speed increases. So therefore, I replaced the constant speed set point of 40 kilometers per hour with a ramp rising with a slope of 1, start time 0, initial output 0. In other words, we will start with the set point of 0, and after 20 seconds, we will have a value of 20, which is here 20 kilometers per hour as a final set point in our experiment. And then we want to consider a few things. We want to consider what happens if we change the center of gravity from the central point forward or backwards. So if AR and IF are equal to each other, the center of gravity is perfectly in the middle of the car. But we do an experiment. First, we load our parameters. Then we sum the AF and AR. We have the total length of the car. And then we say that we have a small AF value. That will mean that the center of gravity of the car will be towards the front. Low AF value, AF is lower than AR, as you can see by this. Then we have a very nice command. It's the command sim. You can use the command sim to run a MATLAB Simulink simulation, a Simulink simulation. You call the model with your full model name, and then that model is simulated. In our case, this is the complete model in which we save the x, the y values, the forces in the lateral direction, and in which we increase our speed from 0 to 20 kilometers per hour. Then we save all the x values, we save the Fy values, the lateral forces. We have these lateral forces, not only one signal, but we have 4 signals. If we would call this value, we would see that we obtain a whole matrix with lots of rows and 4 columns. So this is the Fy1 signal, Fy2, both at the front, Fy3, Fy4, both at the back. We're especially interested in the difference between the front and the back behavior. Therefore, we save this force, which is equal to the lateral force at the front, and we save this force, which is equal to the lateral force at the back. You also see that I take the absolute value of these forces. That's just to ease the comparison. Both forces will all be negative, which is quite logical. As we see here, we are always in this kind of similar situation where the forces help us to move towards the desired rotation angle. But we do this now for AF smaller than AR. We make a figure in which we will have 3 subplots. The command subplot, the first argument says the number of rows you want in your figure. We just want one row. We want to depict all our graphs in a horizontal way. We, however, want 3 columns because we will have 3 graphs. And here we're calling the first graph. 1 row, 3 columns, we want to consider the first. And there we plot the x values against the y values. In the second subplot, 1 row, 3 columns, second subplot, we will plot the front forces. And in the third and last subplot, we will plot the back forces. And then we change the relationship between AF and AR. AF becomes quite large. That means the center of gravity of the car moves to the back. We will have a situation where AF is larger, the center of the gravity of the car moves to the back. Okay, we do just the same here, simulation, save all the values, call the subplots again and look to the command hold on. It means that the existing result keeps in its place and we add other results additionally. We do that for all 3 subplots. And then again, we play with AF and AR. Here they are perfectly equal to each other. AF and AR are both half of the total length. And then again, we have the results. We plot them with the hold on. Now we also use the aspect ratio for the x values against the y values. And we add a legend. First, we did the experiment with an AF smaller than AR. And then we had the experiment with AF larger than AR and AF equal to AR. We also do that for the other subplots. Also be aware of the fact that we only plot the behavior of the forces at the end of the simulation, in the second half of the simulation, because at the start of the simulation we will have some transient effects we do not want to include in our final graph. If we will run this script, we will obtain these graphs. As you see, you have a certain turning radius if AF is equal to AR. If AF, however, becomes smaller than AR, that means that you will put your center of gravity of the car towards the front. AF becomes smaller, the center of gravity moves towards the front of the car. In that case, you see that you will have what we will call understeer. If your car accelerates, the steering radius increases and we always come at a further and further trajectory from the desired trajectory we want to steer in. So we have this so-called understeer. We have an insufficient steering of our car and we have to adapt by adapting our steering angle and increasing our steering angle. The reason for this is that you see the front force is rather low, and the back force is rather big. So how comes? The front force is rather low, the back force is rather big, so we're not actually rotating enough. We do not have enough front force here, front lateral force, to help this rotation, and moreover we here have a lateral force which counteracts this rotation. So therefore the rotation is not exactly what we want, and so if we increase our speed we always obtain a larger and larger turning radius. However, the more dangerous situation is if AF is larger than AR. So that means that our center of gravity is moved towards the back of the car. If the center of gravity is moved towards the back of the car, we have so-called oversteer. The turning radius is getting smaller and smaller and smaller if the speed increases. And if the speed keeps increasing, this would mean that finally the car starts spinning around its own axis. So that is an unstable behavior. If AF is larger than AR, in other words, the center of gravity is moved towards the back of the car, we have oversteer. This oversteer situation is clearly unstable. Large front force which is causing this oversteering situation, a too large front force which is causing this oversteering situation, which has to be avoided at all cost by constructing a car where the center of gravity is not towards the back of the car, but better is a balanced system or an understeer situation which is not unstable, where the center of gravity is towards the front of the car.